Before we start looking at polynomials with more than one term, let's recall even and odd symmetry of functions. And let's look at symmetry from the rule of 4. Now, the rule of 4, remember, is verbal, numerical, graphical, and algebraic. So for a function to have even symmetry from a verbal perspective, we could say that a horizontal reflection of the graph of f looks the same as the original graph. Algebraically, this translates into the notation f of negative x, because that's a horizontal reflection to change the sign of x. And we're saying that the horizontal reflection looks the same as the original graph, so f of negative x equals f of x. If we contrast that with odd symmetry, a horizontal reflection of the graph of f is the same as a vertical reflection of f, if f has odd symmetry. Well, a horizontal reflection is still f of negative x, but a vertical reflection means to change the sign of y. So here we have negative times f of x. So this says horizontal reflection equals vertical reflection. If a function f has this property, in other words, the negative can come out front, then the function has odd symmetry. Odd symmetry is reflection about the origin, rotation about the origin. Meanwhile, over here, this is reflection through the y-axis. The y-axis isn't very easy to see here. I'll just draw it in a little bit on top of the grid. So that's the y-axis there, and this is the x-axis here. So the graph for an even function has y-axis symmetry, or the y-coordinates for points equal spaces right and left of the origin are the same. So if we go right one and up a bit, then we could go left one and up the same amount. So if we went right and up, we would go left and up the same amount. And so this graph would end up looking something like this if the function has even symmetry. Meanwhile, in the odd symmetry case, verbally, the graph has 180 degrees rotational symmetry about the origin, or the y-coordinates for points equal spaces right and left are opposite in sign. So if we go right a bit, up a bit, we go left that amount and down. And so over here we would have a graph that looks like this in order for the function to have odd symmetry. Numerically speaking, if the point a comma b lies on the graph, and the graph is even, or in the even column here, then we change the sign of x and we don't change the sign of y. This point is on an even function. But here, if we change the sign of x, we have to change the sign of y for function to be odd. So if this is a point a comma b, here and here, then this point is negative a comma b, while the point over here at negative a is negative a comma negative b. Okay, so graphically we can see that this has a mirror image. This graph is a mirror image through the y-axis, and if we were to put our point here and rotate at the origin 180 degrees, the graph would look the same. So again, the algebraic definitions and just some of the basic functions that we've seen so far with even symmetry are the absolute value of x, power functions of x to an even exponent, and a constant function. The reason the constant function, any constant function, has odd symmetry is because this is really k times x to the exponent 0, and 0 is an even exponent. Meanwhile, over here, we've seen x to the n, where n is an odd function, odd exponent, is an odd function, and the cube root is also an odd function. Before we take a look still at polynomials, we want to look at the basic building blocks or pieces, terms involved in a polynomial, and these are the power functions. A power function is a function of the form y equals a times x to the n, where a is the constant coefficient. It can be any real number. X is called the base, and it's any real number. And the exponent is any real number, n. N is the exponent. We don't call this n the power. The power is the result of a base raised to an exponent. The resulting output value y may be any real number, maybe only less than or equal to 0, or only greater than or equal to 0. It really depends on the sign of a. So some examples of power functions are y equals 1, y equals x squared, y equals 1 over x, y equals the cube root of x. But y equal to the absolute value of x is not a power function because it's a piecewise function that we'd have to break into the two pieces depending on the sign of the input. So this is not a power function. Just a notation thing. We often see something like 2 to the 3, and we call it 2 to the power 3. We don't read this as 2 to the power 3 because the number up here is an exponent. We can read it as 2 to the exponent 3, or simply 2 to the 3, or 2 cubed. But we want to avoid saying 2 to the power 3 because when we get to seeing logarithms in chapter 3, it can cause some confusion and misconception and misunderstanding. But the result of a base raised to an exponent is a power. And when we talk about the powers of 2, for example, how we buy our hard drives and flash drives, we buy them in 2 megabytes, 4 megabytes, 8 megabytes, 16, 32, 64, 128, etc. These values are the powers of 2 because they are 2 raised to the exponent 1, 2 raised to the exponent 2, 2 raised to the exponent 3, 2 to the exponent 4, 2 to the exponent 5, etc. And what we're noticing is that the little numbers up here are exponents. The result of a base raised to an exponent is a power. And so this quantity, 2, 4, 8, 16, 32, 64, 128, is a power. So if we see 2 cubed or 2 to the exponent 3, the value of the power is 8. So the power is the result of a base raised to an exponent. All right, let's explore these power functions, but let's do a quick comparison between power and exponential functions. A power, as we just saw, is a base raised to an exponent. But we could have a function like x squared or a function like 2 to the exponent of x. In this case, the base is x, the exponent is 2, and the power is x squared. We call this the second power of x. This does not say that the power is 2, it says that x squared is the power, and it's a power of x. Meanwhile, over here, with 2 to the x, we have the base is 2, the exponent is x, and we could still say that the power is 2 to the x. The difference is when the variable is in the exponent, we call this an exponential function. And when the variable is in the base, we call these kinds of functions with variables in the base, these are the functions that we call power functions. Yes, it's correct that 2 to the x is a power, but we don't refer to it as a power function because the variable in the exponent means that we're going to call it an exponential function. If we look at the graphs to compare as well, just to make a distinction in their shapes and behavior, y equals x squared is a power function, whereas y equals 2 to the x is an exponential function. We'll study exponential functions in chapter 3, but for now we just know that the difference is when the variable is in the exponent, we have an exponential function. But when the variable is in the base, we have a power function. So we'll just record this for the lecture notes. Okay, so there's our power function, exponential function comparison. Okay, so this is power function, and it's only one example of a power function, and this is the exponential function. We can have different power functions by choosing different exponents, and we can have different exponential functions by choosing different bases. Back to the polynomial building blocks, the power functions. If we look at several different x to the even power functions, we see that for different exponents of x, x to the 2, x to the 4, x to the 6, etc., we get different shapes of graphs. Let's actually look at these on the grapher so we can see them one by one. Well, we first of all know that y equals 1 is a power function because we have x to the 0 here, and it has even symmetry. We see that there are no x-intercepts when we have x to the 0. Y equals x squared also has even symmetry. y equals x to the 4 has even symmetry. And we should start to notice something that's happening between these intersection points at -1, 0 and 1, 0. We see that we've got a flatter base on the x to the 4 graph than x to the x squared. With y equals x to the 6, it's even flatter. And this is just happening from the numerical table of values. If you take a fraction like 1/2 and substitute it in for x, this value will be 1, this value will be 1/4, this value will be 1/16, and so on. These will get smaller and smaller values. This will be 1/64. And so we can see that the y values are flatter until x equals 1. Then when x is bigger than 1, the y values are bigger, and so the graph is steeper. So the flatness is between the two intersection points at -1, 0 and 1, 0, and then the steepness of the graph increases for increased values of the exponent. And we can see that there's only one x-intercept, but the flatness of each graph is trying to indicate that the 6 x-intercepts of this power function are getting jammed in here. We'll talk more about multiple roots later on. If we look at the odd functions, y equals x is x to the 1, y equals x cubed. We see that these two graphs intersect, this time at -1, -1, as opposed to -1, +1. I think I called this intersection point -1, 0 and +1, 0 before. That's an error. -1, 1, +1, 1. This is -1, -1, and +1, +1. And as we increase the exponent, we see that the blue graph is flatter in between the intersection points, or in between the vertical lines x equals -1 and x equals +1. I don't want to write this in two different equations, so instead of x equals -1 or +1, I'm going to write it as x squared equals 1, and it'll give me the two vertical lines all at once. So in between, on that interval from x from -1 to +1, the blue graph is flatter than the red graph, or the purple graph. And if I keep increasing the odd exponent, I see that the graph gets flatter and flatter, and outside of that the graph gets steeper and steeper. So we see that the x to the 7 graph is the steepest one when x is greater than +1 or less than -1. So that's what this is showing you here. All right, so let's talk about symmetry. The power functions with even exponents have even symmetry. And the power functions with odd exponents have odd symmetry. Let's remember that a power function has the form y equals a times x to the n. So a power function is only one term. We don't have plus something else or minus something else when we are dealing with power functions. As far as x-intercepts are concerned, these power functions have x-intercepts located at the origin or located when x equals 0. The higher the exponent, the flatter the shape of the graph is at the origin. Okay, end behavior. If we take a look at these polynomials and we look at their ends, we are talking about letting x approach -infinity or letting x approach +infinity. The ends means that we are zooming out to look at these values of x. So the end behavior is also referred to as the non-vertical asymptote behavior, and we'll see that more in later section of this chapter. For odd power functions, as x approaches -infinity, y approaches, well, let's take a look at the graph. On the odd graphs, as x approaches -infinity, y is going down towards -infinity. And as we move to the right on these graphs, y is going up. So we have, as x approaches -infinity, y approaches -infinity, and as x approaches +infinity, y approaches +infinity. Using limit notation, then as the limit as x approaches -infinity of x to an odd exponent equals -infinity, and the limit as x approaches +infinity on the right end of the x to the odd power function equals +infinity. We say that the value that the limit equals is the height that y approaches. The value that the limit equals is the height that y approaches. So we're not saying that y equals negative infinity. This notation says that y approaches a height, or the graph approaches a height of negative infinity and positive infinity here. For even power functions, as x approaches negative infinity, just picture a parabola. As x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y also approaches positive infinity from the even symmetry of these functions. The only special case here is if we have the power function of a constant. And so on a constant function, if we just look at the graph y equals 2, for example, well, let me make it y equals 1, just a basic constant function. On the graph of y equals 1, this is the x-axis, and this is the horizontal line y equal to 1. As x approaches negative infinity on this graph, y approaches a height of 1. And as x approaches positive infinity on this graph, y approaches a height of 1. So that would be an exception to the even power functions. So let me just put except x to the 0. Okay, so using limit notation, we can just put a positive infinity here and a positive infinity here. We can also transform power functions, just like every function. So if we apply our knowledge of transformations, we can sketch new power functions that do not just have x-intercepts at the origin. So let's consider this basic power function. We notice that we could put it into transformational form, and we have a vertical reflection and a vertical scale. So we take the graph of x squared. Let's just draw the parent function in blue. Let me put the parent function equation here. Y equals x squared in blue. So 0, 0. We've got some other points we should be able to plot quickly. And I don't have enough height to get up to 9. So we can draw our basic quadratic power function. And then we can apply our transformations of a vertical reflection and a vertical scale. So every y coordinate I'm actually going to multiply by -2. And so we could get our new graph like this. The new graph ends up looking a little bit, oh, I went over too far here. The new graph looks a little bit narrower because the y coordinates are doubled, which means that they seem to go longer than wide. Okay, so there is our transformed y equals x squared to get the power function y equals -2x squared. And if we start off with the basic parent function y equals x cubed, that parent function looks like this. We go 2, 8, -1, -1, -2, -8. And so there is our parent cubing function. And this transformation says to horizontally translate 1 to the right. Sorry, 1 to the left. So from here we go over 1, up 1, over 2, up 8, left 1, down 1, left 2, down 8. And there is our transformed graph. So again, we can apply basic transformations to the parent functions and graph all sorts of functions without creating a table of values. Well, if we look at an exercise 2, we've got function f of x and g of x. Which one is easy, or both, to graph? Because x shows up in all of these different terms, it's very difficult to see the transformations. We can't just state a sequence of operations that have been performed on x. Meanwhile, over here, we could say that we only have to take our basic x cubed graph and horizontally translate left 1 space, or a horizontal translation of -1. So we could graph this one very easily. It is very easy to graph. The other one is not so easy to graph, but if we know some factoring, let me write not easy to graph. And the reason it's not easy to graph is because the equation is not in transformational form. But if we could do some factoring or techniques to go from having written the independent variable in more than one term, if we could do something like completing the square, for example, in the last section, then it could potentially become easy to graph. In this particular case, I recognize that x cubed plus 3x squared plus 3x plus 1 is actually factored as x plus 1 all cubed. So in fact, f and g are the same function. In this form, therefore, this is easy to graph. But if even the constant had been plus 2, then this factoring wouldn't have been correct. But if we get a little bit creative, if we noticed we had x cubed plus 3x squared plus 3x plus 2, we could write that as x cubed plus 3x squared plus 3x plus 1 plus another 1, because 1 plus 1 is 2. And then, of course, this first piece, or 4 terms, is equivalent to x plus 1 cubed plus 1. So we could see a horizontal translation of -1, and then this vertical translation would go across to y, and y minus 1 means we have a vertical translation of +1. So sometimes we may be able to take an expression and rewrite it by factoring to put into transformational form to transform the basic functions. But we have to know our basic factoring from algebra. All right, now that we've done some work with transforming the basic power functions, and remember power functions are only one term, what happens if we add a cubic power function and a quadratic power function and a linear power function and a constant? Then what we get are linear combinations. And we are going to be studying these linear combinations of power functions, which are called polynomials. So if we have power functions whose exponents are 0, 1, 2, 3, the natural numbers, the counting numbers including 0, then we come up with polynomials. The coefficients are real numbers. And the degree, or the order of a polynomial, is the value of the highest exponent on x when the polynomial is expanded. In exercise 3, we're given a polynomial in partially factored form. What is the degree of the polynomial? Well, if we're working hard here, we would take this and expand it all out term by term, and that would be 1, 2, 3, 4, 5, 6, 7, 8, 9 different terms before collecting like terms. But if we want the highest exponent on x when the polynomial is expanded, we simply need to identify the highest degree term in the first factor and the highest degree term in the second factor, and we could just multiply those. We know that 2x to the 11 times negative x to the 10 is negative 2 times x to the 11 plus 10, which is 21. And then we generally write something like this, which indicates lower order terms. Terms with exponents that will be lower than 21. And so therefore the degree equals 21. Every polynomial then has the same end behavior as its leading term. We want to sketch the graph of the leading term, which is a power function. In this case, we have x to the 21, which is odd, and we saw that the odd-shaped polynomials look like this, or like this, depending on whether we have a vertical reflection. This second graph has a vertical reflection. So our polynomial, the graph of the leading term, would look something like this. Very flat, probably, between x equals -1 and +1, because of the high exponent 21. Let's just see a graph that shows that every polynomial has the same end behavior as its leading term. In fact, I'll get rid of this grid, and we'll take a look at y equals -2x raised to the 21, and our actual term, or polynomial, which is y equals 3 minus 4x squared plus 2x to the 11 times 5 minus x to the 10 plus 7x to the 9. In fact, we're going to look at the purple graph first. And it's very difficult to see. I'm going to change the 2D range so that maybe we go -10 to 10 is good, and let's make this -1000 to 1000. The y values, of course, are going to be very big because they are the x values raised to exponents of 21. And if we zoom out, it's still really hard to see. I'm going to make the y values 100,000 and negative 100,000. And I would really like to make the x values not so wide. Let's see if I can make it from negative 5 to 5. Okay, still hard to see, but if we zoom out, well, I'm going to try to change the windows again. If we zoom out and let x become big, this is a very difficult one to see. The 21 maybe isn't a good example. But the graph here, as x is going to the right, y is going to positive infinity, and as x is going to the left, we can't see any of these output values on the graph because when x is 40, 40 to the exponent of 21 is very, very big. But if I turn this graph on, we start to see that as x goes to the left on both purple and blue, y goes to positive infinity, and as x goes to positive infinity or to the right, y goes down towards negative infinity. Let's see this with a bit better example because I want it to be really clear. If I have y equals x cubed and y equals x cubed minus 2x squared plus 5x minus 1, if we reset the graph, we zoom out, we see that the two graphs end up having the same end behavior. Okay, let's move on. Characteristics of polynomials. Polynomials are special functions because they are always smooth, meaning no matter where well, first of all, they're continuous and they are smooth. The fact that they are continuous means that there are no jumps, vertical asymptotes, or holes. The reason for that is the algebra equations have no denominator or domain restrictions. Polynomials do not have a denominator with variables in it, and they don't have radicals or even roots specifically. So there are no jumps, vertical asymptotes, or holes in the graph. So we don't have to lift our pencil off the page to draw the graph of polynomials. Furthermore, polynomials are smooth, even though a function like the absolute value of x is continuous. It's not smooth at the origin because of the piecewise nature. And a graph like y equals x to the 2/3 is called a cusp graph. Now, I want to make a change here. I think I've got a little typo. Obviously, the equation of the absolute value graph is y equal to the absolute value of x. Please make that change in your handout. So here we have a corner at the absolute value of x graph equal when x is 0. And we have a cusp, which is this shape on the graph of x to the 2/3. Specifically, if we look at the graph of absolute value of x, and we try to zoom in at the origin, we know that we will never get a single tangent line. And we have a sharp corner where the left-hand slope and the right-hand tangent slope are different values. If we look at the graph of x raised to the 2/3, or we could call this the cube root of x value squared, if we zoom in at the origin, the graph still never looks like one straight line. Instead, it looks like two vertical lines, but this piece is decreasing and this piece of the graph is increasing. So we do not have a smooth graph here. This shape is called a cusp. But for polynomials, no matter where we zoom in on a polynomial, at any point on the graph, if we zoom in far enough, the graph looks like a line, and that's the tangent line to the curve. So really, when we're saying that polynomials are smooth, we are saying that they have tangent lines. So this is interesting characteristics of polynomials, that they are continuous and smooth for all real values, which is x contained in the reals. All right, now let's talk about the zeros of polynomials. For a polynomial function f of degree n, that means the highest exponent on x in the expanded polynomial is n, and n is a whole number or zero for a polynomial. Then the function has at most n real zeros, and so the graph has at most n different x-intercepts. And the graph of f has at most n minus 1 turning maximum or minimum extreme points. These would be relative extreme values because if the polynomial continues on forever, the absolute minimum is negative infinity and the absolute maximum is positive infinity for y. Here are some statements that are equivalent, and so we may use these terms and words interchangeably. If we have a solution x equal to a is a solution of the equation f of x equal to 0, so therefore what we're saying is that when we substitute x with a, we get f of a is equal to 0. F of x equal to a is a 0 of the function, which is the same as saying a solution to the equation. X minus a is a factor of the polynomial. If that's a factor, then f of x divided by x minus a has no remainder. And lastly, the point a comma 0 is an x-intercept of the graph. So we'll see all of these terms in action throughout this section. In the next exercise, let's sketch the graph of this function by identifying the end behavior, the x-intercepts, and the y-intercept. It is not going to be possible for most polynomials for us to identify the maximum or the minimum points on the graph, and so let's not even try to do that. We'll just approximate it and to find out exactly where those max and min y values are and what x coordinates produce them, well, that's calculus. What we want to notice here then is if we were to expand this, we would get y equals negative x cubed plus some lower ordered terms. So y equals negative x cubed looks like this by vertically reflecting our basic cubing function. And so we know that our graph, which is y equals, sorry, I should put not dot 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 here, but our graph in blue is going to be negative x cubed plus dot dot dot, so it's going to have an end behavior like this with something going on in the middle. And that something going on is dictated by the x-intercepts. We know the x-intercepts are found when y is equal to 0. And if we set y equal to 0, we get 0 equals negative x times x plus 1 times x minus 3. And by the zero product property, that means that negative x equals 0, or x equals 0, or the second factor equals 0, so that x equals negative 1, or that the third factor equals 0, so that x equals 3. This again is indicating the horizontal translation. We would have expected 3 x-intercepts here at 0 on the original function, but now we are getting some translations, 1 to the left, 3 to the right. So these are our 3 different x-intercepts. We can get the y-intercept by setting x equal to 0. And there's no need to expand. We can set x equal to 0 straight away. So we get y equals negative 0 times 1 times negative 3, which is 0. Again, we just needed to say 0 times non-zero is 0. And of course, whenever the x-intercept is at 0, that's also going to be a y-intercept. We know that the graph has to come down first, and we have to turn around. The graph cannot be a horizontal line, so we don't exactly know where to turn around, but it does. And for now, that's as good as we can do without calculus to know where these maximum and minimum interior points are. All right, let's extend this a little bit. Let's look at what happens when we have repeated zeros or multiple roots. In this picture here, we see the graph of the polynomial y equals x squared times x plus 2 all cubed times x minus 1. If we expand this polynomial, we see that we have a degree of x squared times x cubed times x to the 1. This has the same end behavior as x to the 6, so the degree of the polynomial is 6. We have 3 distinct x-intercepts. This first factor, when y is 0, set equal to 0 gives us, we get x squared times x plus 2 cubed times x minus 1. Tells us that we have x-intercepts at the roots, x equal to 0, or negative 2, or 1. So at x equal to negative 2, we see this zoomed in behavior. If we zoom in here, we see this flattening out. And this curve kind of reminds us of the cubing function with a vertical reflection. At x equal to 0, if we zoom in on the actual graph, and I can pull up the actual graph just so that you see it coming from scratch, we have negative x squared, positive x squared times x plus 2 all cubed times x minus 1. And sure enough, there is the graph. So if we look closely here, this graph reminds us of y equals, I won't bother graphing it, but y equals an x plus 2 cubed, but with a vertical reflection. This reminds us of a parabola shape, and when we look at the graph, we take that connection to the algebra, we see that the x-intercept here is 0, which came from this first factor, x squared. So we're seeing a vertical reflection of the x squared here. And then x minus 1, when we look at this looks very linear. There's not much flattening of the graph, which is the same for a linear function. We don't flatten when we go through the x-intercept. Understanding this zoomed in behavior at each of the intercepts allows us to predict the shape of a graph without knowing more about the calculus. So let's apply that to the next function. In exercise 5, we are given f of x equal to x plus 1 squared times x minus 1 cubed times 2 minus x. So we can identify the basic power function that has been transformed by expanding the leading terms. This first piece would give me x squared, the second factor would give me x cubed as the highest, and then negative x. So we get x squared times x cubed times negative x plus dot dot dot, which is negative x to the 6 plus dot dot dot. So we have an even function, so both ends both go up or down, and because of the vertical reflection we know that the end behavior would be this. So this is the graph y equals negative x to the 6, and let me put that in blue because I will draw the given function now in red. So y equals negative x to the 6 looks like this. Well, let's be careful. There's a bit of flattening out. Let me put a 6 here. So the graph is going to be a bit flat through the x-intercept. And so y equals negative x to the 6 plus dot 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 will have some stuff going on in the middle, and the end behaviors like this. This is as x approaches negative infinity, and this side is as x approaches positive infinity. Okay, so sketch as accurately as pre-calculusly possible. What we really need to do here is make a sign chart. And in order to make our sign chart work, we need to recognize these three factors. I'm going to list them over here, and that they correspond to three different x-intercepts. The x-intercept from the first factor is negative 1. The x-intercept from the second factor is positive 1, and the x-intercept from the third factor is 2. I'm going to use very light lines to create regions or intervals of x values. With 3 cuts on the x-axis, I have 1, 2, 3, 4 regions. For now, we have to ignore that the y-axis is there. So I'm going to list my factors. The factor that gave me the root, or the x-intercept of negative 1, is x plus 1 squared. It's important to include the exponent here because that's part of the table of values that you would create when you substitute for x to get y. And then the next root is 1, which came from the factor x minus 1 cubed. And lastly, the factor 2 minus x gave me the root, or x-intercept, of 2. It's important not to call this x minus 2 because 2 minus x and x minus 2 are not equal. They are negatives of each other's, and a negative would cause a vertical reflection, which would change the signs of y. So in each region, I'm going to pick a test value, negative 2, I'm going to pick 0, I'm going to pick 1.5, and I'm going to pick 4. I'm going to take these sample x values and substitute them in one at a time. I'm going to do it kind of quickly, so you might want to pause the video and see what happens when you substitute these numbers in. Negative 2 plus 1 is negative 1, all squared is positive. But in fact, any number that I plug in, except for negative 1, if I take negative 1 for x and sub it here, I get 0. 0 squared is 0. But I'm not taking negative 1 for x because that's a boundary or root x value. In between the regions, I'm taking test values, which will always make this base positive or negative. Squaring it will always make the result positive. X minus 1 all cubed. Well, when x is less than 1, taking any sample values, substituting it in and cubing gives me negative. These two values give me positive. And 2 minus x, well, 2 minus negative 2 is positive. 2 minus 0 is positive. 2 minus 1.5 is positive, and 2 minus 4 is negative. what I notice is the first factor times the second times the third is f of x or y. So the result for y is the product of all these signs in each region. So in the first region, y is positive times positive. I don't really need to worry about the positives, I just need to count the number of negatives. So y will be negative. In region 2, y will be negative. In region 3, y is positive, and in region 4, y is negative. So what that's telling me is that when x is less than -1, y will be negative. So therefore, y will not be positive or lying above the x-axis. I'm going to draw my graph in red. In the second region, y is negative, so y will not lie above the x-axis. The graph will not be there. In the third region, y is positive, so the graph lies above the x-axis or not below the x-axis. And in the last region, y is negative, so y is not positive. The graph does not lie above the x-axis. So here's my y-axis, here's my x-axis, and I've got 3 x-intercepts. I can also work out the y-intercept by substituting x with 0. And if we do that, we get f of 0 equals 1 squared is 1. I don't need to write that down. -1 cubed is -1, and 2 minus 0 is 2. And that actually is very good news because it's in the unshaded region, which means that the graph does lie here. I'm going to go now and erase in the regions where the graph is going to lie, just so it's not too messy and too hard to follow what's going on in here. Okay, so now we want to draw the graph. And we recognize that the regions are consistent with the end behaviors. This is like a giant puzzle and all the pieces have to go together. The only last thing we have to be concerned with is what kind of shape happens here. At the x-intercept -1, the graph has to turn around. And that makes sense because it's got even behavior, so the turning around makes it look like a parabola, even though it's concave down. Then at x equal to 1, it looks like we would probably go smoothly through, like a linear, except for the fact that we've got a cube here, which means that the graph should flatten out a little bit more. So we won't go smoothly through. At x equal to 2, the factor that gave us that is 2 minus x to the 1, which will go smoothly through because it's like a linear function at that piece. So the graph is going to do something like this. Now, we don't know where the minimum point is. We have this point plotted, so it's possible that that's the minimum, and it's right in the middle of these two x-intercepts, but we shouldn't make any assumptions. I'm actually going to consider that my minimum point is lower than that, and then, I don't know, maybe draw the graph like this. Lower first, and then hitting the y-intercept on the way up. That's going to give me time to flatten out for my cubic piece, then turn around somewhere and go smoothly through. Another possibility is that people could have drawn the graph coming like this. There's lots of possibilities. We don't know exactly how the graph is going to go, but either the red or the blue, the black graph would be acceptable. You could also make the y-intercept the minimum point, but chances are we didn't find the minimum point just by luck, by it being the y-intercept. Let's take a look at the graphing program and see how we did. Without knowing where the maximum and the minimum points are, we can only use pre-calculus techniques, and that's what I mean when I say sketch as accurately as pre-calculusly possible, without actually knowing where the maximum or the minimum points would be. So knowing about the x-intercepts and their zoomed-in behavior, knowing about the y-intercept, and knowing about the end behavior of the function. We get something like this. Oh, we weren't bad. The red one looks a little more accurate. So we'll keep this picture. I'll turn it to red so it looks like my hand-drawn one. And we'll add it to the lecture notes. Okay, there's a third part to this question. Let's use the graph to evaluate the limit as x approaches negative infinity of f of x and the right end behavior. Let's put it on here. According to this, as x goes to the left, y is going down. So the limit as x approaches negative infinity of f of x equals negative infinity, and as x goes to the right, y goes down, and so the limit as x approaches positive infinity of f of x equals negative infinity. Again, remember that the value that the limit equals is the height that y approaches. The value that the limit equals is the height that y approaches. So when y approaches negative infinity, we say that the limit equals negative infinity. All right, the next thing we want to talk about is the intermediate value theorem. Theorems are very convenient mathematical pieces of knowledge because someone has done the hard work to prove the theorem, and our job is simply to make sure that the theorem is applicable or applies because the conditions of the theorem are met. If that's the case, we get the result of the theorem and someone else's hard work for free. The intermediate value theorem states that if a function is continuous, so if it has no holes or jumps or vertical asymptotes, if it's continuous on a closed interval where x goes from a to b, and we're going to say that a is less than b, so on a number line, a is on the left and b is on the right, then the function takes on every intermediate y value from f of a to f of b. So if x is equal to a on the function f, then I should say if a function f is continuous, we want to relate it to this letter here. When x is a, then the y-coordinate is f of a, and when x is b, the y-coordinate is f of b. So let's take a look at some clarifying questions to really understand the intermediate value theorem. In exercise 6, answer the questions below and use a sketch to illustrate your answer. Does the intermediate value theorem say that f of a must be less than f of b? Well, it says that we're choosing a to be less than b, so that on the x-axis, a is left and b is right. But it doesn't say that f of a must be lower than f of b. We could have on a graph that the y-coordinate f of a is less than the y-coordinate f of b. But we could also have that the y-coordinate f of b is lower than f of a. This just means that overall from a to b the graph would increase or decrease. So no, the intermediate value theorem doesn't say that. Either of these two sketches is appropriate. All we're saying is that a is on the left and b is on the right for the x values. Okay, so we'll clear that up and we read our graphs from left to right. Now we want to ask, does the intermediate value theorem state that for the x value of c between a and b, that the corresponding y value must be between the y values of f of a and f of b? Well, let's draw a picture to understand this a little bit better. We have x equals a and x equals b, and c is somewhere in between, and let's say that this is f of b and this is f of a, so that when x is a we have the ordered pair here, and when x is b we have the ordered pair here. We notice that we have a horizontal line of y equals f of a and a horizontal line of y equals f of b. Must f of c lie in between here? That's really what the question is asking. The intermediate value doesn't say that. The intermediate value theorem says that all heights between f of a and f of b are in the range. But it doesn't really say that if x is c, that the y value cannot be outside of that range. So let's take a look at part C. Does the intermediate value theorem say that y cannot take on y values outside the interval? Again, that's the same issue. If we have our two boundary y values, y equals f of a, and y equals f of b. And we have an x-coordinate here of a, and we have an x-coordinate here of b. It doesn't say that when x is c, that the height can't be higher. It doesn't say that the graph can't go like this, or that the graph can't go like this. The graph can do all sorts of variations on the theme. It could go directly there, but what we do notice is that as long as the graph is continuous, and we don't lift our pencil up to go from the first point on the interval to the second point, or the last point on the interval, it's definitely saying that every height in between the boundary heights gets taken on. There is no way to get from a height of f of a to a height of f of b without going through every height in between. Every single height in this vertical range must get taken on. But we can still go beyond the range, go higher or lower than the two known y values for the two given x values. So the intermediate value theorem does not say that the graph cannot go higher or lower than these boundary values. All it does say is that if I know my graph goes from, let's say, a height of y equals -3 to a height of y equals 5, then if the function is continuous, then there's no way to go from one height to the other without taking on every other height in the range. So every height here has to be taken on. Can the graph go higher or lower? Yes, it can. But every height must be taken on from a height from -3 to +5. And so the last clarifying question for the intermediate value theorem says, if f of a is negative and f of b is greater than 0 or positive, what implications does this have on the graph of f for some x value? Well, let's just say when x is a, that we have a height of y equals -3. So we have a point here, a comma -3. And when x is b, we have a height of y equals 5, for example. And there's lots of ways that I can move from this point to this point on a function that is continuous. I could go directly there. I could do some kind of horizontal, constant, piecewise function thing. I could go higher. I could zigzag a lot. There's lots of different ways. Let me just draw a very simple function. Something like that, without making any assumptions about being one-to-one or only increasing, etc. Well, the most significant thing that I notice from a pre-calculus point of view is that this function has an x-intercept. And this is absolutely crucial because of the intermediate value theorem. The only way for a continuous function to go from a negative height to a positive height is to pass through a height of 0. And keep in mind that the equation of the x-axis is y equal to 0. So we will use the intermediate value theorem oftentimes when we want to talk about finding x-intercepts of a function that is continuous, given that we know the function has some negative y values and some positive y values. Every y value in the interval from a height of -3 to a height of -5 must be taken on, including a kind of special height of 0, because that height of 0 represents the x-axis, the x-intercept. So we use the intermediate value theorem a lot when we are looking for x-intercepts. There's one last exercise, exercise 7 in this lecture, and we will save this for the recitation. I would like you to think about how the intermediate value theorem can be applied to answering part A and B before coming to class. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. Please put these questions on a separate piece of paper. And that's all for now.